Hello, is everyone here? Hello. So currently I'm seeing Rahul, Subrita, Arpan, Manisha, Tiyasha. So as far as I can see, Subrita, Arpan, Manisha, Tiyasha. So as far as I can see, Aditi is not here. Debargo is not here. Two of them gone. Tiyasha is here. Radhi is not here. So 9 of them, right? Shubrita is here, right? Tiyasha is here. Shubrita is here. Tiyasha is here. Anisha, Shabina, they are here. Priyadarshini is here. Arpan is here. So Aditi hasn't joined. Debargo hasn't joined. And Raghiv hasn't joined. 3 of them didn't join. 6 and Pritam and okay. Let's start. So what were we doing in the last class? I think we are studying box topology and quotient topology, right? Sorry, and product topology.
রেকর্ডিং চালু করে দিয়েছো?
Thank you.
ঠিক আছে।
So yes, actually in the last class I gave you a formal definition of the Cartesian product. Like, I mean, how did we define it? If there is an say, like there are sets a1 to an and product ai running from 1 to an, we write it like an ordered pair. So basically elements here are like a tuple, like so it's like a1 up to an, where ai is coming from capital A, right? So also actually we defined it in the following way, like these are actually functions from the set 1 to n to union ai such that a of I belongs to ai, right? This, I mean, we have written down in ordered pairs, so we are just considering this tuple to be a function a which is from 1 to n to union ai such that a of I is in ai. See, these are same, right? These definitions are same. But what is the power of this definition? The power of this definition is that we can extend this definition of product to an arbitrary indexing set. So let product ai we are defining where I belongs to j. J is an arbitrary indexing set. So we can define it like a from j to union ai such that a of I belongs to ai. Okay, so this is the formal definition of product, and we have defined like the box topology here just as we defined in the product topology. I mean, product spaces, there were two theorems I mentioned in the last class. Like the theorems were like where are the product spaces?
Page number 116.
Thank you. না না আমি প্রোডাক্ট স্পেস চাইছি
ও আচ্ছা আচ্ছা প্রোডাক্ট স্পেস
it was like this. Okay, so there are three theorems. One is like this was one of the theorems, like the product topology on x cross y, like x is a product topological space, y is a topological space. This was a definition of the topology of the product space. What was that? We are taking open sets from x and y, we are producting them, and we are considering the product topology on x cross y to be the topology generated by u cross v, by this basis u cross v, where u is open in x and v is open in y. So this is one thing, keep it in mind. This is the definition. Also we had some other things like this was a subspace, right? I mean subbasis. What was this? X cross y projection maps pi 1 was to x and pi 2 was to y, and we took inverse images of pi 2 inverse of u where u is open in y and pi 1 inverse of v where v is open in x. Union of that set actually formed a subbasis. Okay, so this was another definition. Why am I going through this? Because we are going to find analogous definitions in arbitrary product spaces. Subspace topology. Okay, now let's move on to here it is. See, just look at this definition of box topology. This is exactly analogous to the the topology on product spaces for finitely many cases we read that. Now you might ask that why it is not called the product topology, or why is it called the box topology? I'm telling you that. I mean, say this is an open set in y and this is an open set in x. Okay, so what is the Cartesian product? The Cartesian product is the following space, right? This is a box, that's why it is called box topology. We will talk about product topology in a moment, but just go through this definition and realize that this is basically the analogous to an analogous definition to what we did in the for finitely many spaces. Okay, so this is the definition of blocks topology, and see there are analogous results like product of u alpha intersection product of v alpha is just intersection of is the product of intersection of u alpha intersection v alpha, that is intersection of product is the product of intersections. So then there are projection maps they have defined, like from product x alpha to x beta, where just x alpha is a tuple. Here x alpha is a tuple, and the projection map, the betath projection map is basically nothing but the projection onto the betath coordinate. See, again this is a sub basis. See, now this generates the product topology. Read this definition. See, we have seen already that, I mean, for finite cases, this definition and the previous definition we have seen for x cross y when there were only two spaces, that these two, this subbasis yields the same topology as the basis does. I mean, basically box and product are same for finitely many products, for finite products. See, I will take you to that thing again. So this is the definition of a box topology, right? What is that? They are just taking open sets from each of the topological spaces x alpha, and they are doing their product, and they are defining box topology to be the topology generated by this basis. Okay, so this is the definition of box topology. Now what they are doing to define the product topology, so basically they are taking open sets again from x beta from each topological space. Now they are considering the inverse images of these elements u beta. Now they are considering the union, right? This generates a topology which is called the product topology. So let's get back to the previous product space definitions again and see what we were doing. See, this was our product topology, right? Open sets from each of these spaces and producting them, right? And we observed that this thing, this also yields the same thing, right? We have actually observed that this is a sub basis. What is this is S1 and this is S2, right? In our notation right now, and this generated the same topology, the product topology on x cross y, right? So for finitely many cases we might say that the box and the product topology are same. Pritam, clear? Pritam, clear? Hello. Am I muted? No, yes. Hey Pritam, তোকে জিজ্ঞেস করছি
No.
clear কিনা? Okay, so Okay, but how are these two different for arbitrary product? Let's see. So how is it actually? Do you remember the definition of a subbasis? I mean, what is a subbasis? Do you remember it?
ইউনিয়ন করলে ওই স্পেসটা পাবো।
Yeah, but how did we define the subbasis topology? That's what I am asking. The definition of a subbasis, basis of a topology. Where is subbasis? Here it is. See, read this definition very carefully. Okay, so you are taking elements from subbasis. You are basically taking the finite intersection of in those elements. Now taking arbitrary unions, right? So arbitrary union over finite intersections. That's how we generated the topology, the subbasis topology, right? So why I am going back and forth, because I just want you to connect well with what we are doing right now with uh, what we did previously. So let's try to compute how this product topology looks like, or maybe how this subbasis topology looks like. Okay. So suppose we are taking S to be union of S beta, right? Where S beta is pi beta inverse U. Raghib, don't be so late.
Yes, sir.
Okay. Okay, so let's try to have a look at the finite intersections. So let u beta and v beta are open in x beta. Okay, so what will it look like? How will it look like? This is nothing but this. Okay, check this step, check this step. But this thing is again in s beta, right? So we are not getting any element outside s beta. So now let's take u alpha belongs to x alpha and u beta belongs to x beta, and try that how does it look like. And if we do this intersection, what is it like? Okay, first of all you tell me what is the intersection of this thing. Let say x beta belongs to capital X beta. So what is this thing? What is the fiber of this? Fiber means the pre-image of this. What is this thing? Can anybody tell me? Tell me for finitely limited cases at least. Suppose this is the product. Okay. And I am taking say pi 3 inverse x3, where x3 is in capital X3. So what will it look like? What should be this thing?
ওই x1 x2 x3 করে করে xn অব্দি প্রোডাক্ট
such that pi 3 of eta equal to x3.
এইটা হবে, right? This is the product, right? Right. This is supposed to be the product, na? Because every element here, I mean elements here are of this form, y1 up to y2 x3 comma y4 up to yn, where yi belongs to xi, I not equal to 3, right? So pi 3 of any such element, y1 y2 x3 y4 yn is x3. So pi 3 inverse of x3 are all these elements, right? So this is the product. So for this, what will happen if the indexing set is, say we have taken x alpha, alpha belongs to j, arbitrary product belongs to pi beta is the projection map, then what should we get like pi beta inverse x beta? What should it be for x beta belongs to capital X beta? What should be the product? Just like before, for the beta coordinate it will be singleton x beta, and for the other coordinate this will be the whole spaces, right? So we can write like this: a alpha alpha not equals to beta, where a alpha is x alpha if alpha not equals to beta, and a beta is singleton x beta, right? This should be the case, right?
হ্যাঁ
Okay. open now. So what is this thing? Pi beta inverse u beta, where u beta is an open set in x beta. What is that? That is again product of A alpha. Alpha belongs to, sorry, alpha belongs to J, where A alpha is x alpha, alpha not equal to beta, and A beta is u beta. That's what we should get. Okay, but we did take, this is our alpha, right? So now similarly, if u gamma is a subset of open pi gamma inverse u beta, gamma will be similarly where A alpha is x alpha, alpha not equals to gamma, and A gamma is u gamma, right? So what will be the intersection? Anybody? What will be the intersection?
Only beta and gamma coordinate will be decided by u beta and u gamma.
Pi beta inverse u gamma.
Hmm? You can't do pi beta inverse u gamma. I mean,
এটা
sorry.
পাই গামা ইনভার্স হ্যাঁ
Right. So he says this
এটা
is going.
বি
So he is saying that this is supposed to be this. Again, I mean, if you want to do a rough work here, like again, for finitely many cases, suppose this is our product. So what is, suppose u1 is open in x1 and u3 is open in x2. So we know that pi 1 inverse u1 is like this, u1 cross x2 up to xn, and pi 3 inverse u3 is like this, x1 cross x2 cross u3 cross x4 up to xn. So the intersection pi 1 inverse u1 intersection pi 3 inverse u3, it will be like u1 cross x2 cross u3 cross x4, this, okay, xn. So this is the product. So just as this, we are writing the exactly same way A alpha, where A alpha is x alpha for alpha not equals to beta gamma, and E alpha equals to, sorry, A beta equals to u beta, A gamma equals to u gamma, right? This will be, so this
Yes.
is a new element, and this is not in S. This is not in the subbasis, right? Elements of subbasis are of this form, not, so this is a new element we are getting. This is a basis element, but not in the subbasis, okay? So just like this, see, they have taken the finite products, finitely many product. Read this, read this bracket. Just a minute. Hello. না পড়াচ্ছি, ওই জাস্ট বলছি যে সোমবার তো যাওয়ার চেষ্টা করবো, এবার যদি সোমবার সংকট দেখ, সোমবার আমাদের বন্ধ থাকে, সংকটটা আজকে তো সংকটটা আমাদের যদি ফোন করে এসো আমি থাকতেও পারি, সোমবার হলে সব থেকে ভালো হয়, কেউ থাকবে না, তা না হলে ওই মঙ্গলবার করতে হবে। হ্যাঁ মঙ্গলবার থাকে, মানে বুধবারও থাকে, কিন্তু বুধবারটা তো আবার দেখি না, না পড়ে দেখছি। আসলে কি জানিস তো, যখন খুব বেশি চেঞ্জ করলে না ঝামেলা হয়, মানে এবার বারবার যদি চেঞ্জ করি একটা সময় একটা অ্যাডভান্টেজ, তাড়াতাড়ি শাড়ি থাকলে চেঞ্জ করি, মানে আজকে আমার অসুবিধা হচ্ছে চেঞ্জ করতে, ওই জন্য খুব বেশি চেঞ্জ করতে আমি চাই না। হ্যাঁ ওই তো ওই পেছনটার জন্যই তো বলছি। এটা পড়িয়ে নিই just a minute। Oh, sorry, sorry. I read this actually. I shared some other.
The mic off.
Sorry, tell me when this page is done. Actually, I some other I shared some other screen actually. Nothing. They have just extended the idea from two to finitely many. So this is the idea. Now let's
The screen is not visible.
screen is not visible. No, it is visible actually. Screen দেখা যাচ্ছে না?
হ্যাঁ দাদা দেখা যাচ্ছে।
Yes,
Rajesh,
visible.
okay, your connection might be doing some stuff. You can actually exit and then rejoin.
Okay.
তাহলে দাদা আগেরটা থেকে আমরা এটা প্রুফ করলাম যে ওই ধরনের এলিমেন্ট গুলো বেসিস হতে পারে না।
Hmm? No, they are in the basis. They are just not in the sub basis.
হ্যাঁ মানে সেটাই বলছি, হ্যাঁ
They are
ঠিক
in the
আছে।
basis, but not in the sub basis. This is alpha belongs to J, A alpha, where A alpha is equal to X alpha, and alpha not equals to beta I running from 1 to n, and E alpha equals to, sorry, right? So this is how open sets in product topology looks like. Open sets in finitely many coordinates, the rest are the whole spaces. First we make an observation. Observation 1. Let's name this actually U, call it U. U is open in box topology. Okay, no, first let's write down that box topology. Basic open sets in box topology are of the these are more easier to look at. Alpha belongs to J, right? I mean, sorry, alpha belongs to J, where U alphas are open in X alpha. Okay. Now we make the following observation. Call it अच्छा था। U is open in box topology. Is it true? Is it true that any open set which is open in product is also open in box? See, U is open in box topology. Why is that?
প্রোডাক্ট টপোলজিতে ওপেন হবে তো
Which one?
ইউটা
Yes, U is open in product topology. Of course, that's a basic element. But is U also open in box topology? I am trying to see whether if any topology is finer than the other. See,
হ্যাঁ হ্যাঁ হবে
right? Because what is U? U is product A alpha, right? Alpha belongs to J, and A alpha is X alpha. Alpha not equals to beta I, and A beta I is U beta I, right? Now see, U beta I's are open in X beta I, right? And X alpha is open in itself. So this belongs to the basis as well. Okay. It implies box topology is finer than product topology. Okay. So whenever we are talking about X alpha, we shall assume that the topology is product topology unless stated otherwise. So this is the basis of the box topology. Fine. Read this to this. Example 1 and above that. Please go through it. One thing is clear, I think. If J is finite, if the indexing set is finite, then box and product are basically same. So which brings us A alpha is a subspace of X alpha. These are, this is a very important result. See, okay, so I expect you to go through this at home. Okay, I will go through the concept here, but the technicalities I expect you to go through at home, and if you are stuck, please tell me. Okay, read this at home. I tell you to read a lot of stuff at home, but I never come across any doubts from your end that we actually studied this and we are stuck here. So either you are doing very good, so you don't have any doubts, or you are doing very bad. See, this is a very important theorem, because of course, after what do we define after defining the open sets, or I mean, what is the goal of defining open sets, or in the topology, what is the goal of that? The goal is, of course, to study continuous functions. So here we are trying to give a characterization of function spaces, characterization of functions into the product space. I mean, A is an arbitrary topological space, and product X alpha is the product space. They are trying to give a characterization on of the functions onto this. First, let us get back to the theorem where for finitely many products were there, continuous functions were there, I think. Yeah, this was the theorem. Maps into product spaces. So this was the characterization of continuous functions from a topological space to a product space. So is there a similar result here? Let's see. So X alpha is be an indexed family of subspaces. A alpha is subset of X. No. If to product X alpha given by this equation, if alpha is are just, you understand na, if A is a tuple, right? Because it is inside this. So if alpha is are just component wise elements, product topology, then the function is continuous if and only if alpha is continuous. Okay, you will see most of the results of the product spaces for finitely many finite product will actually have its analogous for when the product is given the product topology, but not in the case of box topology. We will come on to that, but again please read this at home. Pritam atkale bolo, Shubrita, Raghi, I mean those who are appearing for jam, I am telling you, since this is okay, I mean others are in M.Sc, so they might have gone through this once, but go through this. If you are stuck, please tell me. See, there is no shame if you are not understanding something. I don't understand a lot of stuff. I think all of us don't understand a lot of stuff, so that's not an issue. Okay, we will go through this example very carefully. See what they are trying to do. what is the goal here? They are trying to come up with a function which is component wise continuous, but not, I mean, they are trying to show that this above result is not true when product x alpha is given the box topology. That's their goal. So what they are doing, they are considering a function if from r to r omega. What is r omega? R omega is, this is nothing but r cross r cross r, okay, countably many times. So the function is just the diagonal, like t is going to t comma t comma t comma t. So the coordinate wise functions are continuous. F and t is going to t, so the coordinate wise functions are continuous, right? Because n belongs to z plus, which is natural number. So you can also think about this like the set of all real sequences. So of course you can see like each fn is continuous because f is from r to r omega, or maybe r to the power n as you prefer to write. And suppose you are taking the nth coordinate, I mean nth component, nth projection. So this is fn, right? It is continuous, right? Since fn t is t, so fn is from r to r and fn is continuous. Each coordinate function is continuous, therefore the function f is continuous on r omega when r omega is given the product topology. By the above result, it is continuous when r omega is given the product topology. But when it is given the box topology, what happens? See, they have taken the point, 0 0 0 0 0, okay, in r omega, okay, and they have considered this ball, I am writing it as O for origin. This ball is a neighborhood of O, right? This ball is a neighborhood of 0. But their claim is that F inverse beta is not open in R. This is their claim. Like claim F inverse B is not open in R. The proof is pretty simple actually. If it is, proof, suppose F inverse B is open in R. 0 of course belongs to F inverse B. So there exists delta greater than 0 such that 0 belongs to, I mean some neighborhood of 0 will be inside this, right? Subset of F inverse B, right? But there is a problem. Why this cannot happen? Because then f of minus delta comma delta is inside B, right? But what is f of delta comma delta? This is minus delta comma delta cross minus delta comma delta cross this, right? Countably many times. Right, this is the image of delta comma delta, na? What does it mean? Minus delta comma delta cross minus delta comma delta cross, this thing is inside 1 comma 1 cross minus half comma half and so on, right? So this means that minus delta comma delta is a subset of minus 1 by n comma n for all n belongs to natural number. Pritham, is it clear?
Yes, sir.
because each bracket should be inside these brackets. But what does it mean? It implies delta is less than 1 by n for all n belongs to natural number. That is delta is 0, which is a contradiction because delta was better. Okay. See, the very, I mean, the first function that we think about when we are actually going from a space to a product space, these are like inclusion functions, right? Or maybe these diagonal functions. I mean, even the fundamental, I mean, the very trivial functions, they are not continuous. So you might have to, I mean, if you are in an interview, they might ask you to give an example. This is your homework. I think you will be able to do it. One of the implications. What was 19.6? Okay. So 19.6 has an if and only if part, right? Like if is continuous, if and only if product x alpha is given the product topology. So they are saying that one implication is continuous, and which one is that? So we have just seen that this implication is not right because each fn is continuous but f is not continuous, right? So each fn is cont but f is not. So but is the opposite true? But what about the following, that f is a function from a to product x alpha. This is given box topology, and f goes from a to f alpha of a, alpha belongs to j, and each if and if is continuous, then each if alpha is continuous. Is it true? This is a one line proof, right? Take f, take a,
F compose
yes,
pi alpha করলেই হয়েছে।
if compose pi alpha, no? Pi alpha composite.
হ্যাঁ, pi alpha composite।
We know that these pi alphas are continuous, right? Sorry, maybe I should write pi beta. So we know that pi beta is continuous. So if beta is pi beta compose f is continuous. Okay.
দাদা আরেকবার লাইনটা দেখো। বলছি প্রোডাক্টে যেমন ইফ অ্যান্ড অনলি ইফ ছিল, এখানেও তো ইফ অ্যান্ড অনলি ইফই হবে বক্স টপোলজিতে।
How? We have just shown in the previous example that even if f alpha is continuous, f is not
না না
continuous.
না না হবে না, ভুল বলছি।
Okay. So let's
হয়ে
move on
গেছে।
to the next problem. See, I'm not expecting that you will do the whole exercise, but at least you should get some idea. X1, X2 is sequence of points in the product space. Show that the sequence converges to the point X if and only if the sequence phi alpha X1 phi alpha. I expect you to do this. R infinity with a subset of this we will do, because actually I am willing to finish this exercise today, and we will move on to the compactness connectedness. This is one of the problems. This is not needed. ABS set X alpha in this family. Show that there is a unique courses topology tau. Let f alpha be the index family of functions f alpha from A to union X. So there is a unique courses topology tau on A relative to which each of functions f alpha is continuous. This is also a very good problem. Okay, but let's try to do this. Let's try from 6. See, I give you 2 or 3 minutes to try. Do any one of 6 and 7, and then I am coming back. 2 to 3 minutes. x1 x2 be sequence of points in the space. Show that the sequence converges to x if and only okay.
একটা পার্ট খুব ট্রিভিয়াল না, x1 x2 xn যদি x এ কনভার্জ করে আর পাই আলফা গুলো তো কন্টিনিউয়াস, তাহলে তো পাই আলফা অফ x1 ও x এ পাই আলফা অফ x এ কনভার্জ করে।
Why? She is saying that, see, how does x1 look? x1 is a sequence of point in the product space. So x1 is a tuple, right? x1 is like this. Similarly, each xn is a tuple. She is saying that if xn converges to x, then pi alpha xn should converges to pi alpha x. That is your argument, right? Since pi alpha is continuous, but there is a trick. But the problem is that sequential criteria for continuity is valid if the space is Hausdorff, right? We have proved it for the Hausdorff space.
হ্যাঁ,
But is product x alpha Hausdorff? আমি বলছি no, as any two open sets wait a minute, is it Hausdorff? Any two open sets intersect in this, right? Or okay, let's try to prove. Let x is a tuple, y is a tuple belongs to pi x alpha such that x is not equal to y.
স্ক্রিনটা বন্ধ হয়ে গেল।
হ্যাঁ, না না সবই ঠিকঠাক আছে। Beta belongs to j such that x beta not equal to y beta, right? Since they are not equal, there has to be a coordinate in which they do not agree. As is it, but it is not also told that if
হয়েছে এবার?
okay, it is not also told that each product x alpha is Hausdorff. It is not also given that whether each x alpha is
Yes,
Hausdorff or not. Tina, এত সোজা না বুঝলি? You cannot just use it all together. If each x alpha is Hausdorff, then there exists u beta, v beta such that x beta belongs to u beta and v beta and y beta belongs to v beta, and u beta intersection v beta is phi, where u beta v beta open in x beta. So then I am telling that this x alpha belongs to u, where u is product a alpha, alpha belongs to j, where a alpha is x alpha, alpha not equals to beta, and a beta is u beta, and y alpha belongs to v, where v equals to a alpha equals to j, a alpha equals to x alpha, and a beta equals to v beta. Check that u intersection v is phi. Okay, check this. This is very easy actually. What will be u intersection v? This will be product a alpha, alpha belongs to j, where a alpha is x alpha, or alpha not equal to beta, and a beta will be u beta, intersection what? V beta, right? So this is nothing but so this is phi, you understand that? Check that this is phi. Suppose something is in the intersection, then there will be the beta coordinate has to be in u beta and v beta, and check that this happens. Okay, so you can't all of a sudden use that continuity argument, so it is not true. Okay, use this result to prove it. I expect you to try this at home. This thing 19.5, use 19.5 to do it. More than the solution of the problem, I think the discussion is more important. What about 7? What about 7? First of all, tell me whether you understand the question or not. Is the question clear to you? R infinity is the set of all eventually zero sequences. It is a set of all n belongs to natural number, such that n is 0 for some n greater than equals to n naught. N naught where depends on the sequence. Okay, so this is the definition of R infinity, and R omega is just all real sequences or countably many copies of R. So what is the closure of R infinity? So let x alpha,
এটা ইউনিয়ন 0 0 0 হবে, মানে এটা পুরোটা ইউনিয়ন 0 0 0।
the puroটা union 0 0 0. She is saying that what about this union O, where O is 0 0 0 0. Well, I have a doubt. My claim is this: R infinity closure is whole R omega. So let's see. Let x alpha belongs to R omega. Okay. So there exists U open in R omega such that x alpha is in U, right? U is of the form, I am taking this to be the basic open set. ठीक है? U is of the form what? U is of the form product U alpha, alpha belongs to J, where U alpha equals to X alpha for not equals to, suppose beta I, alpha not equals to alpha I running from 1 to n, and U alpha I is these are proper open sets. Okay, open X alpha. This is how a basic element in the product X alpha looks like in the product topology. We are considering the product topology. So is 000, I mean sorry, is, does this U, does is U alpha, or what is U intersection R infinity? What is it? What is U intersection R infinity?
On
Hmm?
the
I can't hear you. Oh, we don't have to take this J, because we actually can take alpha belongs to natural. শুনতে পাচ্ছি না।
আর ইনফিনিটি হবে।
No, actually what I am trying to say is that I am saying that define y alpha by alpha belongs to natural number such that y alpha I is in u alpha I, okay, I running from 1 to n, and y alpha is 0 if alpha not equal to alpha I. Okay, we can define y alpha like it. See that y alpha belongs to R infinity, isn't it? As y alpha is 0 for all alpha greater than maximum of alpha is. অনিশা বোঝা গেছে? Raghiv, is it clear what I am doing? Shubrita? Am I disconnected?
as এর পর কি লিখেছো?
As y alpha is 0 for all alpha greater than equals to this. See what I am doing. I mean, this is, suppose, I mean, u alpha 1 and u alpha n, okay, and there are some things behind it, some things before it. So I am saying that y alpha should be like this: y alpha 1, y alpha n, and 0 after that. Shubrita, clear? Why y alpha is in R infinity? তুই সব থেকে বড় আলফা এটা নে না, তার থেকে বড় তো সবকটাই 0 হচ্ছে না। হ্যালো
হ্যাঁ দাদা।
Raghiv, is it clear? So y alpha is also in U, right? Implies not equals to 5. Closure. Okay. But in the product topology, there might be, I mean, in the product topology, there might be some issues, because like if x alpha is in R omega, okay, then actually we can, so we can take x alpha belongs to product u alpha where
স্ক্রিনটা দেখা যাচ্ছে না।
স্ক্রিনটা দেখা যাচ্ছে না? কি বলছিস রে?
আমি বলছি প্রীতম,
তোর নেটওয়ার্কের সমস্যা আছে, তুই কেটে বেরো, কারণ স্ক্রিন, আই থিঙ্ক দ্য স্ক্রিন ইজ ভিজিবল টু এভরিওয়ান, রাইট?
ঠিক আছে।
So I am trying to say that not all points here if r omega is not inside r infinity, then what do we get? I mean, let's write xn actually, enough of this alpha. Rahul, what will happen? I am thinking that it will not, it shouldn't be the whole set actually, but then for that I will have to. This is not in R infinity, right? So what does it mean? It
Yes.
means that uh, xn is not equal to 0. I mean,
after finite
after
points.
finitely many,
Hmm.
after finitely many terms, that is xn has a subsequence xnk, k belongs to nk belongs to natural number such that xnk not equal to 0 for all nk. Is it clear?
Yes.
Is it clear to everyone? I'm specifically asking the BSc students. Somebody has commented something probably. Okay, Shubrita, is it clear?
হ্যাঁ দাদা
If xn is not 0 for after any finite number, so for each finite number we get an xn which is non-zero. We are basically collecting those and making a subsequence, that's it. So there will be, for n equal to 1, there will be a term say xn1 which is not 0, then after 2 there will be a term which is xn2 is not 0, and so on. Okay, so there exists del nk greater than 0 for each nk belongs to natural number such that minus xnk belongs to minus del nk, sorry, ank comma bnk bnk belongs to r such that xnk belongs to ank comma bnk and 0 is not in it. Okay, right? There is a neighborhood which skips 0 of xnk. Now u equals to, we are defining u to be un n belongs to natural number such that un is unk is ank comma bnk and un suppose is r if n is not equal to nk. Then u intersection r infinity is phi. This is my claim. Can you see? Can you see why it is in phi? Because if I can't hear you. There exists n naught belongs to natural number such that yn is 0 for all n greater than equals to n naught. This means y nk is not in unk for all nk. I mean for any nk. For any nk greater than equals to n naught. Right? So R infinity closure is R infinity in box topology. Is it clear? Is it clear?
হ্যাঁ
The intuition should come naturally to you. That's my only point. What about
So
it?
yeah, that's my question. Actually, here it is given R infinity, but if something other set is given, then how to come up with such
Now,
claim?
see, this is an intuition. Okay, you will have to grow this intuition by practicing this thing. This will not come after just first reading or second reading. R infinity is a
Or is
standard set. Whenever we are talking about R
it
omega,
very much necessary? I mean, after mm,
see, I mean, after a while, we will prove a certain thing. I mean, why R infinity is so important? We will show that R infinity is connected. Okay, and we will conclude that hence R omega is connected in product. That's the, I mean, see, these are uh, they are not going to invent a new set for you in the examination hall all of a sudden. Okay, so there are actually I mean few spaces which you will have to play with.
okay.
The chance is very slim that you will come across a new space in the examination hall. I mean, even if it is a new space, I mean, it is not actually a new space. It might be in the periphery of your knowledge. It should be in the periphery of your knowledge.
Mm, okay.
Okay. What about 8? A1, A2, Bn are real numbers. A is define R omega to R omega by this. Show that if R omega is given topology, H is a homeomorphism. Is this obvious? One part is obvious, I think, right? For the box topology, it is for the product topology, it is obvious, right?
Yes.
So H is continuous in box in product topology as Hn, that is pi n compose H, is continuous, where Hn,
H
yes please,
F লেখা হয়েছে
where Hn is just from R omega to R omega, it is just x1 xn an xn plus b. So complete it. Okay, write H inverse H inverse you should be able to do it, right? Just compute component wise. Write H inverse to complete. Write H inverse to complete. But what about box topology? What about box topology? Anyone? What about box topology? Any intuition? Should it happen? Should it not happen?
Not even. I think the
Not
example given
Yes,
before
yes, 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 yes.
will work here.
But you will have to, I mean, in some way make some adjustment, right?
Yeah, yeah.
He is saying about this example, the last example. He is telling me to use it. See, these are also linear functions, right? So he is telling me to use this. Let's see how we can do it. So this is H. So if H is continuous, mm,
আরবিটারি ইন্টারসেকশন অফ ওপেন সেট ইজ নট ওপেন, এখান থেকে কন্ট্রাডিকশন পাবো।
use to করতে হবে বাবা। What is H
তো
inverse?
এই
What is H inverse?
এই ইনভার্স হচ্ছে x1 x
I mean, the idea is same
x1
basically. I mean,
x1
suppose
x2 xn such that ওই h of ওটা ইকুয়াল টু ওটা, তো x1 x2 xn যেখানে পাই ইনভার্স অফ h এর ইন্টারসেকশন গুলো থাকছে।
so we can solve this to get that, right? I mean, I'm trying to say this. This is 0, right? Or I mean, this is the image is 0, right?
Yeah.
We are actually trying to do what we just did. So we will take,
We'll take the neighborhood about this point.
yes, but each inverse of that point it is just computation, nothing else. রাহুল এটা কমপ্লিট করে পাঠাতে পারবি?
Okay, I'll try.
Okay, okay, so he will try to complete the proof and send it. If you
Yeah,
can't
yeah.
do it, then I will actually this is just computation. You have to come up with a neighborhood. I mean, this should work actually. This should work, the one we previously took it.
এটা আমি যেটা বললাম সেভাবেও করা যাবে। ধরো z ইকুয়াল টু x1 x2 xn, ঠিক আছে, তাহলে ইনভার্সে কারা থাকবে? ধরো z belongs to rw such that pi 1 of fz belongs to, ধরো এগুলোকে u1 u2 un নাম দাও, তো pi 1 of fz belongs to u, pi 2 of fz belongs to b। তো ওগুলোতে থাকছে মানে ওদের সমস্ত কিছুর ইন্টারসেকশনে থাকছে। তো সেটাকে এবার pi 1 of
That's the thing. In arbitrary intersection is no. তোর argument ভুল। I mean, you can't say that arbitrary intersection of open set is not open. You can't say that. At most, you can say that arbitrary intersection of open sets need not be open. Right? But you are assuming that it is never open.
আচ্ছা
That's the flaw here.
আচ্ছা
Okay, so try to complete it. If not, then I will actually send it. শ্রীনা পারবি এটা চেষ্টা করে দেখিস।
আচ্ছা ঠিক আছে।
আনিশা ক্লাস বোঝা গেছে? আগের দিন রেকর্ড করতেই ভুলে গেছি, ভাবলেই এত বিরক্ত লাগছে কি বলবো।